Hi everyone, thanks for tuning in again. I'm Alfredo, and today I want to talk to you about the actor model for concurrency and Akka, an implementation of the actor model on the Java machine. Now, why is this important? Why do I want to tackle this subject? Well, because in software engineering, you will eventually come into situations where you have to solve the problem of high availability. So a lot of times you will have to set up and deploy systems which are deemed to be mission critical or what's also called tier 0 in the industry. And that effectively should never go down, or rather, should be virtually always on because they serve many important stakeholders, because you're providing a service to customers, or because it is effectively a system that supports certain systems on top. Now, in the 80s, Ericsson, which is a company that you may be already familiar with, had to face a very similar problem, specifically because they needed to deploy phone switching infrastructure across the United States. The switching infrastructure was deemed to be tier 0, and it had to accommodate not only for any kind of elasticity, and not only it had to remain functional all the time, but it also, the whole project also had the explicit intent to accommodate for the rise in telecommunications usage that will be to come in the following decade. So out of their efforts, the Erlang programming language and runtime came out of Ericsson. And this solved the problem of high availability through a very sophisticated and very interesting approach to concurrency. Basically, which is the actor model, actually. This approach to concurrency encapsulates business logic in self contained small units of computation called actors. Think of an actor as a process on a Linux machine, a PID, but an actor has completely isolated state and is self-reliant, so it can spin up or spin down copies of itself to accommodate for elasticity, for scale, in case that you need to run more tasks in parallel over time. The characteristics of the actor model, to start getting a little bit technical about this, by the way, actors are coordinated but by what's known as a supervisor. This may sound similar to virtualization supervisors, which is a similar concept in a way, but not exactly the same concept. Now, actors communicate in a runtime through message passing, and they have a unique address that other actors can use to refer to them, and they have a message queue which is used to receive traffic from other actors, to buffer messages from them. Then any specific actor grabs messages at their leisure from the queue, from the message queue that they have in front of them. Now, another characteristic is that if an actor runs into an exceptional state, well, an actor should be let to just crash. And this is one of the most sophisticated things about the Erlang runtime, that indeed it allows you to run software with very amazing concurrency without deep re-engineering of your current code practices. If a process just crashes, then the supervisor has strategies to spin up the process again, to resume the process, or to take whichever other outlet it may. This leads eventually to very resilient and very robust concurrent systems which can accommodate massively for scale. And this led to their success with the AXD 301 deployments that they have. So, today I would like to show you a small example on the Akka implementation of the actor model. There's a library available commercially called Akka, which used to be included in Scala, which is a purely functional language for the Java machine. But it was abstracted out and vendor to other people through our library. So it is available for use for anyone who needs to develop this kind of system on the Java machine. All right, so this is where the magic happens. Think of here on the actual main method, which is the de facto beginning of execution in Java code bases. I am instantiating an actor system by passing it a module. This greeter main, it's a class. Think of it as a module which defines what an actor should do. The class is abstract behavior, and you literally have to extend it. What it should do when it gets a message of a certain type, like here, or when the actor is actually created. Very simple stuff. I'm trying to just to remain very simple leveled here. My plan is to eventually follow this up and to make it more complicated. Okay, and finally, at the actor system level, I start passing a message, and the message would just contain a string. This example right here is a very friendly system whose only concern is to greet people. How does it do it? Well, once I get a message of the hello type, then I'm gonna call this and just spawn an actor for this and send it 3 greetings. So now let's run this. And if we jump onto the command line, let's run Gradle here, which is what I have. And you will see how Akka creates the actor system. Then the user actor creates a greeter actor, sends a hello, this spawns another actor here, name it depending on the string that I send, and then Charles replies just by keeping tally of how many greetings he's gotten so far. This logic is in the greeted. This logic is in this greeter factory class. Greeting number such and such. And as you can see, every actor has independent state which is never shared. What happens if we come to the quick start example here? Let's copy this line. And if we add, several different invocations here, for example, for Albert and for Albuquerque, then once we run it, you will notice that it's going to start sending messages, not necessarily in order, because of course this may have a race condition. The order is not necessarily guaranteed, which is known as a race condition. And at the same time, this may or may not affect your system. Usually for systems like this, it shouldn't. And commonly you just want to process some kind of user request on a one-by-one basis by a certain actor in your runtime, then normally it shouldn't matter. But in some problems, for example, if you're doing some kind of scientific calculation where order is of the essence, order of operations, then yes, this is something which you may actually have to work defensively about. And I am gonna follow up this video with an addition as to how to make an actor throw an exception and self-heal such a way that if you were to have an exception here which is not caught, then it's going to bring the whole system down. But again, one of the main characteristics of the actor model is that if a single actor has a certain exception, it shouldn't bring down the whole system. So I'm thinking that's everything for now, but let me know what you think of the example so far. This stuff has been really fun to look into, to dive deeper into. So I hope that it's useful for you. Feel free to drop a line in the comments, and I guess I will be seeing you around in the next video. Take care.